And okay, yeah, and yeah, and so welcome everyone. So so the quick seminar is now moving online, and we're happy to have Aram Harrow here today. And so the format that we're having is we're thinking of having a 1-hour talk and then 20 minutes of informal discussion afterwards. And the informal discussion is kind of meant to, to let Aram meet a lot of the other people at Quicks, kind of as if he were on a real visit. So during the talk, if you have questions, maybe the best way is to enter them on the group chat, and then when it's convenient, then maybe we can pause the talk and Aram can answer some of the questions. And then afterwards, during the informal discussion, then we kind of like more natural back and forth discussion. And yeah, and so on that note, let me introduce Aram. So he's at MIT and he's done a lot of work on many different areas of theoretical quantum information science, including quantum algorithms, complexity theory, Shannon theory, and a number of more applied topics related to quantum computing. So today he's going to be talking about hybrid quantum classical algorithms, and he actually had a number of other results that he was also willing to talk about, including results on Hamiltonian complexity and communication complexity. So you're welcome to ask him about those after the talk. And so let me hand it over to Aram. Thanks very much.
Great, thanks Ikai, and everyone for coming to this. I'm sorry I couldn't be in Maryland in person, but I guess if I would just be Zooming from a hotel room in Maryland, so that wouldn't do much good. But someday we'll all meet in the quick seminar room in person. I want to tell you about 2 papers. I mostly prepared this talk thinking I'd talk about my recent paper, and then I realized I've done some other sort of related work on hybrid classical algorithms with John Knapp from a year ago, which I might briefly mention at the end. But you may be more familiar with. My recent work was motivated by trying to think about how could a quantum computer help with machine learning if we know that a lot of classical machine learning uses big data sets. But quantum computers do not seem to really enjoy working with big classical data sets. And so this work represents my attempt to grapple with that. And before I get into specifically my results, I want to just talk briefly about how we should think about quantum algorithms. Because if you read papers in the quantum machine learning, like papers that have come out in quantum machine learning, it's sometimes a little confusing to know what is achieved, because to understand what's achieved, you have to know the input model that they're using. And the quantum algorithms literature sometimes moves fluidly between these different input models. And I think it's not made explicit enough often, so I just want to be very explicit about it at the beginning. So I'd say the standard input model is, the very first one you learn in a complexity textbook. When you have a Turing machine with a bunch of bits on a tape, and then you output a single bit, and it's fairly straightforward. The input, you could think of as the input as you have a fixed program that takes some input, or maybe a more reasonable version for a quantum computer is you have a classical program that looks at the input and then uses that to build a quantum circuit. And that's sort of the common sense notion of how a quantum computer would work, which is you have a laptop that looks at your data and then issues a bunch of instructions to whatever, the FPGA or the pulse programmer to control the actual quantum hardware. And examples of this are factoring, the number theory problems, combinatorial optimization. So you might be searching over a very large search space, but it's described succinctly. Like if you have a 3-sat instance, the clauses of that 3-sat instance tell you, the 2 to the n possible, I'm saying that badly. If you have 3-sat, you have 2 to the n possible strings, right? And you want to know which one satisfies the most clauses. But your input is not a list of all that truth table of 2 to the n, how many clauses are satisfied by each of the possible true to the n strings. Your input is just a list of clauses, this very succinct input that can then be used to build up the whole truth table. Okay, so that's the standard input model, is you have a reasonable size input, so you get the whole thing either on tape or somehow given to you, and then you give an output. Now, it's often useful to think about the oracle model instead, where instead of having the input given to you explicitly, you have implicit access to it, meaning you have a function, an oracle O, that has random access to the input data. Yeah, tell me if you're, yeah, maybe I should stop now. If you can't hear me well, speak up. Okay, maybe it's just Eddie.
I don't know. Sometimes it just drops. Just
okay.
It was okay on my end. It may vary.
Okay, so good. Hopefully it's not widespread. So in the oracle model, you can think of the input as maybe extremely long, maybe exponentially long, and you have an index I that tells you which part of the input you're querying. And so a lot of quantum algorithms like Grover search, the NAND tree, the collision problem, the hidden subgroup problem, as well as sort of more esoteric ones like the quantum walk on welded trees, these all use the oracle model, and this can be really useful in terms of giving us provable speedups is a really nice feature of it, and letting us talk explicitly about structure. So you can say, hidden subgroup problem is a very abstract thing. It says for any function where the the input has some kind of periodicity, the quantum computer can find that, and it really makes sense there to take as input. You could think of it as your input is a function rather than a string. And then even more sort of uniquely quantum models, there's the model of quantum data. So instead of your input being a classical string, it could be a quantum string. And this is when we talk about the quantum Fourier transform or Hamiltonian simulation, these implicitly have a quantum state as input. The swap test computes the inner product between two states, is using quantum input. And here, people also talk about Q sampling and how this quantum data is sort of analogous to a classical sample. And in some cases, you can do similar things with it, like, estimate the mean of some quantity. And in some cases, like with the swap test, you can do way, way better with quantum samples than with classical samples. State tomography could be thought of in this area. The linear system solvers, I guess they use a mixture of quantum data for the input state and an oracle to specify the matrix. So they kind of mix two of these models. And the final one that combines both of these is you could have a quantum oracle. So you're given access to a large unitary transformation and you want to do something with it. And this is, of course, super important in many cases. One of the most important is phase estimation. So given you want to find, estimate eigenvalues of it or try to do a measurement in the eigenbasis. And that's what phase estimation does. Very important algorithm. Quantum sensing and process tomography are other examples of doing this. And sort of a more modern and generalized version of phase estimation are the cubitization and singular value transforms. If you know what those are, if you don't know what those are, then don't worry about it because I won't refer to them, but those can all be thought of as very sophisticated things to do given a large unitary transformation as input. So there are many different models, and what can we, different algorithms use different of these models, and it's important to be clear about which one we're using when we're trying to evaluate what an algorithm is doing. And so one algorithm which is, I think quite, so yeah, one very old algorithm is Grover's algorithm, one of the oldest ones. And I think it's very exciting because it's so general. It says, if I have, well, you all know what most of you should know what Grover's algorithm is. I have a function, and I'm going to write the truth table of the function. I'm going to think of it as a string, x1 through xn. So I have the ability to compute f of I, and I'm going to call that x sub I, and I want to find the marked I star such that f of I star is 1. So You need order n time classically, root n time on a quantum computer. And we have similar speedups for many other kind of search type problems. It's important to note that this problem is in the oracle model, where the input string is not given explicitly. It has to be given as a function that can be evaluated. And this, I think, threw a lot of people off because of the original title of the paper, which was called like Quantum Search of a Database or something like that. And Grover's algorithm, of course, is a great algorithm, but really not appropriate for database search, as I'll get into in a minute. So, right, so this is an oracle search. We have this oracle subroutine that computes x sub I. That's how we have to use, that's what we need for Grover's algorithm. But this is what an actual database looks like. This is a data center. And this does not look like an oracle, right? We can't query that in superposition. If we ask it about bit 3 and bit 100,000,027,000,027, we cannot send a superposition of requests for those two locations because the data center will break that superposition. So we cannot Grover over this, for example, for one record that meets some condition. And even if we could, that would not be the most efficient way of doing things, because classical memory, you think of it as sort of random access and the CPU is going through it one step at a time. But really, when you scale it up enough, it sort of has to be parallel, because associated to each little bit of memory, you have to have a CPU, and that ratio is not growing in an unbounded way. So as you're scaling up the storage, you're usually also scaling up the CPUs. And so if you want to look for one record that met some criteria, you probably would do that search in parallel. And one way around this is to say, maybe I could propose new hardware, a quantum RAM, a QRAM, that could be queried in superposition. And that has been an approach used by a fair amount of work in the machine learning literature, quantum machine learning literature. But I wanted to see what you could do without it, because quantum RAM is asking more of the hardware designers. And I feel like asking them for a conventional model quantum computer is already a pretty big request. And so I would like to just see what we can do with that. If Chris Monroe can get 1,000 trapped ions that are controllable really well, that's still not a quantum RAM, right? So, and I want to be able to say something about what can you do with a computer in that model without needing to change the hardware model. Theorists are cheaper than experimentalists, so we should be more flexible. Good. So, but how can you do that? Like if I say, look, I have a classical hard drive, that's where my data is stored, x1 through xn. If anyone has a better suggestion for an oracle picture, let me know. This is my picture of an oracle. I would like to turn that into an oracle that I can query, in the sense I mentioned. You give it a quantum register in state I, and it coherently extracts x sub I. So I only know one way to do that in general. Actually, some people from Microsoft have a more sophisticated way of doing this, which I probably should be citing, but it only is going to shave off it's only a little bit more efficient than this. And it's basically, this fairly gruesome circuit where you have a quantum gate, a controlled operation where you say, if the first register is 1, then you add xi to the second register. If the first register is 2, you add x2 to the second register, and so on. This can be done with a small quantum computer, right? Your quantum computer doesn't have to be as big as the hard drive. You just need a little controller that step-by-step goes through the records on the hard drive, converts them into quantum gates. So you have to say, if I equals 17, and then you look at the 17th cell on the hard drive and figure out what x sub 17 is and what the quantum gates for that are. And so you don't have to, your controller doesn't have to have it all in memory, but you do have to be able to step through it. So that is the only real way I know how to do that. And that conversion, of course, is kind of terrible, right? So if you have this order n overhead to every query, that's going to really wipe out all possible Oracle speedups. And so what do you do about that? Well, you could, the first one is to ask for better hardware. And that is an answer, but that's not the one I want to pursue. The other one is you say, well, I just need to come up with a really clever choice of function f. So if my string x1 through xn is not an arbitrary string, but it's the output of some efficiently computable function, like let's say f of I is a to the I mod n. That was Shor's idea in coming up with Shor's algorithm. Brilliant idea. You feed that into period finding, and you can factor the number, and that's great. But it's obviously limited, right? Because in the 25 years since Shor's algorithm, we have not come up with a steady stream of insights like Shor's original insight. And those insights are necessarily going to be limited. Like the actual messy data I get from some real world source is not going to fit this model. And yet still I want to analyze it. I want to ask if the quantum computer can help. So instead, I'm going to talk about an approach where we try to reduce the size of the data set and apply this to sort of classic machine learning problems like clustering, Bayesian inference, and saddle point optimization. So these are pretty general purpose problems where which can be hard, and you want to see kind of a quantum computer help. And so I'm going to talk about how to do that by using data reduction techniques. Any questions before I proceed? Okay, so let me get a little more technical and talk about the type of problem I would like to solve. So the problems I want to solve involve doing a kind of statistical analysis using a data set. And the difficulty of it is going to come both from searching over the space of models and from the size of the data set. One example of such a problem is maximum likelihood estimation, although I should probably change this. I think someone who knows statistics more than me told me it was maximum a posteriori estimation. Those are pretty similar though. So given a set of models Y and a data set X, you want to maximize basically the likelihood of seeing this data set given a particular model. So you're going to maximize over Y. Little y is one of the models. And what you want to maximize is the probability of seeing this data set. You assume these are each independent points. So you just multiply the probability of seeing each data point given the model. And it's often convenient to work with the log. So if you take the log of the probabilities, and then we'll call that f of xy, is the log of the probability of seeing x given model y. The sum of those is like the log of the total probability of the data set. And then this term r of y, you can think of as a prior over your models, or as a regularizer, some term that puts in to say that maybe, before we've even seen any data, we prefer simpler models, or something like that causes us to prefer some models over others even before we've seen any data. Okay, so this is a very, very general problem that we might like to solve. So how can Grover help us with this, right? Grover is a very general algorithmic technique. This is a very general problem. Let's see how it goes. So the first thing to notice is the maximum over y and the sum over x are both things that you can get a Grover speedup for. I mean, there's a few details about how precisely you want to do the sum, but roughly speaking, they're both things where there's a square root type speedup. So if you just look at the math, it looks like the x and y appear fairly symmetrically in this expression. However, the type of data is very different. The data set X lives on a hard drive. These are a bunch of records that you got from real world data or wherever you got them from. These are not things that you can access in superposition. Whereas Y is the set of models is a synthetic set. This might be weights and centers of clusters if you have a clustering. And those you can access in superposition. So the set is much, much larger than the little index that points into it. And you can easily prepare a superposition over this index. And whatever you can evaluate for one model, you could also evaluate for a superposition of models. So that is very asymmetric. And what that means is the straightforward way to get a Grover speedup here is if you have a classical computer controlling a quantum computer, and it's sort of the usual model, then you can speed up the search over Y but not the sum over x. So the runtime would go like the size of x times the square root of the size of y. And what that would look like is the outer loop is maximizing over y. Technically, the algorithm is due to Jur and Hoyer, but I'm just going to call it Grover because it's, sort of use similar ideas. So you'd have this search over y in the outer loop. Classically, you'd have to look at the size of the set y. Quantumly, you only need the square root of the size of the set. The inner loop, you have to evaluate this cost function, and essentially there's no quantum speed up there. You just have to iterate through all the values of x. And so that's what yields this runtime. Now, I'm going to focus for concreteness on Grover in this talk, because it lets me just say explicitly what the runtime is. But this same idea applies to whatever your favorite optimization algorithm is. Like, suppose you think the adiabatic algorithm is going to exponentially speed it up. Then, or, have some dependence on the size of y that's much better than square root of y. That's great. You've improved this y term by a lot, but that x term is just sitting there, and in that case, it's even worse, right? If the bigger your speed up is in terms of y, the worse it is that you also need to multiply by the size of the data set x. So whatever your optimization algorithm is, that is going to be a problem. And so the key question is, how can we reduce the dependence on the size of the data set x? And there's an answer to this from classical machine learning, where they always want to do everything. You always want to do things as efficiently as you can. And one approach is to take your set x and approximate it with a smaller set called a core set. This originated in computational geometry, but has since been applied to machine learning. So if you have like a clustering problem, you have all these points, you'd like to find clusters for them, you could replace all these points with this smaller set of points, and the resulting clustering would look pretty similar. And what it means, more concretely, x prime is a core set if for all models y, the true log likelihood of y is pretty close to the log likelihood we get just from summing over the core set. And here we need this term w of x, which is a weight. So it's actually not just a subset, it's a weighted subset. And the reason is we've reduced the number of points by a lot. So the total number of, that's sort of the naive reason, is kind of the total magnitude of each side would change if you didn't have large weights on these points. But there's another reason as well, which is if you think about a clustering problems with some clusters with a lot of points and some clusters with a few points, actually this weighting question also shows you why uniform sampling won't work. Because I think the natural approach is to say, well, look, if you have a giant data set, just about take a random subset and look at that and run your algorithm there, and maybe that'll give you a good approximation. And if you have a clustering problem where you have some small clusters, if you just uniformly sample the points, that will not work, because a uniform sampling will only hit the big clusters and you'll leave out the little ones altogether. And for some applications where you're looking for where the anomalies are what's interesting, for whatever reason, like mostly at the LHC you see the same old particles, but you want to see if anything new pops up, right? Whatever reason, then that's not acceptable to just throw away all the small clusters. And so what that means is you have to pick the points in the smaller clusters more often than you pick the points in the bigger clusters, but then their weight should adjust for this to make this an unbiased estimator. So actually, I have a slide on that talks about that in a little more detail. So I'll come back to that in a little more detail, but basically that is the idea of a core set. Is it something that's smaller that can give you a good approximation of the original data set. So the high-level picture of how this works is as follows. You start with a big data set X, you feed it to a classical computer that crunches it down to a smaller data set X prime, and then the quantum computer can do some optimization over that and output a model Y. So concretely, how does the classical computer do this? There are a lot of possible ways. One of them is to use a very crude approximation algorithm for to get an approximation y prime. So for example, you might output a clustering that has not only is not the best clustering, but also uses way more clusters than you want. Like you're looking for a clustering into 5 clusters, we'll cluster it into 50 initially. Then you use that to construct importance sampling weights, which tell you with what probability you should sample each point in your data set. So if they belong to a rare cluster, you want to bump up their probability. If they belong to rare, I mean a small. If they belong to a very large cluster, you can give them a small probability because there are many points and you're pretty confident that you'll get one of those. So that's called importance sampling. And you use that to draw x prime. Then, once you have x prime, use whatever optimization algorithm you like, Grover, quantum walks, whatever, to find y. Now the cost of the inner loop just goes like x prime, size of x prime. And so the Grover speed up over y now becomes more significant because the thing you're multiplying by, x prime, is a less dominant part of the runtime. And this yields speedups for, I've been talking about clustering as an example, because this is one where this framework gives you a provable speedup. Provable in the sense of, we know what the runtime bounds are, and this is better than the best known classical algorithm. So maybe I'll say a little more concretely how this importance sampling works. So our goal, remember, is that for all models y, the true log likelihood is close to the approximate log likelihood. And there are a few criteria we have that we need. The first is that you can think of this as an estimator. You're trying to estimate the true log likelihood with a, by choosing the right x prime. And this should be unbiased. So in expectation over my choice of x prime, this should give me the right answer. The second one is I also want the variance to not be too large. So the fluctuations over x prime should not be too large. And finally, this should work not just for one y, but for all y simultaneously. And how do we do this? So the first, to make it unbiased, what we do is we choose some probabilities, s of x, which is a measure of how important each point is, or how important each point is. So points in very small clusters should be very important, so we make s of x high for those. Points in large clusters are individually not very important. But then the weight of each point, if we choose to sample it, should be 1 over s of x. And so the fact that weight balances out the probability of accepting x means that we get this unbiased property. Then, to control the variance, one way of doing it is to choose s of x to be larger than this quantity on the right-hand side here, which is sometimes called the sensitivity. And so let me walk you through that expression. The sensitivity, this is for a point x, is the largest fraction of the log likelihood that that point could contribute to any model. So how important is this point individually to the total likelihood of a model? So you see here, the denominator is the total log likelihood of a given model. The numerator is the contribution just from that one point, and then we want to maximize this over all models. So that is the sensitivity of a point x. Now the tricky thing is you can see that to evaluate this, you have to maximize over the models and sum over all the points. So to evaluate this for a single point is basically as bad as our original problem. So you cannot do this accurately. But it's enough to get this stuff to work to have s of x be an upper bound for the sensitivity. And then use those s of x as your probabilities. And it turns out that the size of your core set will depend on the s of x, on these s's. So you could always choose a really crappy one by just having s be really big, and then you would satisfy this condition, but you would just have a big core set. And the better an approximation you can make, the smaller the core set. But what's nice about this is if you have a crude approximation, that makes your core set bigger, but at least still the final quality of your final answer will still be good. And then to address the third one, where you want this thing to work simultaneously for all y, well, one thing you could do is a union bound, but if the y's come from some set which is more structured, like for clustering, there's some geometry to it, then you want to use something that's kind of like VC dimension to say, well, the set y is, it's that kind of, the complexity is bounded in a certain sense, and there's something called pseudo dimension that sort of tells you about the complexity of the set of models, and this also influences how large your core set has to be. So when you put it all together, the size of the core set you need looks like capital S is the total sensitivity, so the sum of all these S of X's. Epsilon is the error that you're allowing in your core set. D is the pseudo dimension. Delta is your failure probability, and this tells you how large your core set has to be. And what's important about this expression is that it does not depend on the size of the original data set. It just depends on details of your problem. Sorry, that's not true. Capital S, of course, involves a sum over the entire data set. So I'm getting ahead of myself here. A priori, capital S could depend on your input size. And so this bound could be vacuous. It could just be, look, you got to sample the whole data set, you're toast, right? So a priori, this does not tell you anything helpful. But if the total sensitivity is not too large, this can yield something independent of the size of your data set, or weakly dependent on the size of your data set, and that can lead to big savings. And I think I don't really want to, so for k-means, for example, do this briefly. K-means I have in D dimensions. I want to, my model Y is the position of the k centers of my clusters. My f of xy is basically the distance to the closest cluster center. And it turns out the pseudo dimension goes like D times k, times log k. The sensitivity only scales with k, the number of cluster centers, not with the total number of points. And so we get this expression for the size of my core set, which does not depend on the size of the original data set. And this gives me an algorithm, which is the classical computer can estimate S of x for each point x by using some crude clustering to do it. And I'm leaving that part out because that's sort of in the classical literature. Then the next step is either a brute force classical search or a Grover quantum search. And here, the power of Grover is really relevant because we've sped up the rest of it. And so now that most of the runtime is in a brute force search, quantum can really improve things. So this is one way that data reduction can be an effective way of solving a real machine learning problem with a big data set like clustering. So I guess that was one. Yeah, if there are any questions, this is maybe a good time because I'm about to move on to a different algorithm.
Oh, actually, Aram, sorry to interrupt. Can I ask a question? So I was in the process of typing it into the chat window, but
yeah, please. There's always this unmute delay that there's always in Zoom. Go ahead.
Yeah, no, I was just wondering, can you get smaller core sets if you don't care if they're accurate on all models, but you only care that they're accurate on models that fit the data fairly well?
Right. Yeah. Very good question. So we don't actually need. So I was saying all models because I'm thinking about also both maximum likelihood, but also Bayesian estimation. And the if you just want the maximum, then that's right. You have a weaker requirement on your core set, which is that you only have to, exactly what you said. You only have to be accurate on the maximum and on the best one. And on the other ones, you can be a little inaccurate as long as you're not so inaccurate that you think that they're better than the best one. And I don't, people talk about this in the literature. I've forgotten when this gives you savings. In some cases, it gives you savings. Yeah, and let me just not get into the details because I've forgotten them, but definitely in some cases, this can give you some further savings. I see some questions in the chat online. When the data set is small, isn't the speed up also small? And I guess I would say when the data set is small, you don't have to do this core set thing. The speed up then will depend on how hard the search problem is. Right? Like for 3SAT, the data set is quite small. The number of clauses can be quite small, but it's a very hard problem. And I would say that's sort of the situation the quantum algorithm designers are more comfortable with, where you're not really worried about input size too much. You're really worried about this hard combinatorial search problem. And then I thought this data was classical, so why is it available to quantum queries? So yeah, it's good to be concrete about this. After we've done the core set, we still have to, we still have this smaller data set, and then we still have to work with that, kind of in the painful way, like this horrible circuit. And the only good thing about it is that we've really cut down on the size of data that the quantum computer has to look at. I hope that answers the question. Feel free to unmute if not. Okay, so right, so this is an algorithm. This is kind of the flow of it again, and it's fine. It speeds things up. Speed ups are good, but my job is a quantum algorithms designer, and I don't not like how the role of the quantum computer here is not very glorious. It's like the classical computer is like the mama bird that catches the worm, brings it back, chews it up, and feeds it to the quantum computer, which is like the baby bird. And we kind of know the classical computer is going to be acquiring the data. That's like going out and catching the worm. But it's really, the role of the quantum computer is not, you can say that by the time we've turned on the quantum computer, a lot of the hard work has already been done. So what about a model that looks like this, where there's a series of messages back and forth, and the quantum computer can say, I really liked, tell me more about this kind of data point, or here's what I want to know about more. Send me more like this. Is this a way that a quantum computer can sort of adaptively interrogate a large hard drive, a large data set? And I'm going to tell you about two algorithms for this. One of them is fairly general, but a little bit more of a heuristic. The other one has a provable guarantee, but is more specialized. So the problem I want to consider is Bayesian inference. A lot like maximum likelihood, except now, instead of outputting the most likely model, we want to sample from the posterior distribution on models. So we have a prior pi0 of y. We have got the same log likelihood showing up here that tell us how to, kind of reweight this distribution to get some posterior distribution pi of y. And we want to sample y from this distribution. So here's how an adaptive algorithm is going to work. You have, in step T of the algorithm, you have a core set that you're building up record by record. It consists of data points x1 through xt with corresponding weights, w of x1 through w of xt. You send those to the quantum computer, and it samples from the posterior distribution, not from the true data set, but from this core set. So this core set gives you this approximate log likelihood that you see here. This gives you a distribution pi sub t, and we sample y sub t from this distribution. So that is how you're always using the quantum computers. You're always using it to solve this sampling problem. And again, there are many quantum algorithms for this. There's you can get a quadratic speed up of rejection sampling. That's sort of the analog of Grover. You can use quantum walks. So I wrote a paper with Annie Wei about speeding up simulated annealing. So simulated annealing is a good way of doing things here. because then, it's way better than brute force search. And you can, there's sort of a quadratic quantum speed up of that too. It's quadratic. Some parts get quadratically sped up, some parts don't, but hopefully the hardest part gets quadratically sped up. And then, using the stuff that the quantum computer passes back, you extend your core set. You choose one more data point. So you're not just using the important sample weights that you got at the beginning. This is informed by what you're getting back from the quantum computer. And there's a model proposed by Campbell and Broderick, which they have some analysis of, but it's like their analysis depends on parameters that are hard to estimate. So I'm just going to call it a heuristic, but I think it's a reasonable one, and I'll tell you how it works. So to model y, you assign the basis state ket y, and then every data point you can think of as a vector in this space. So phi of x is just the sum of all of the y's for different models with the coefficient given by the log likelihood. And then the exact log likelihood, the thing that you want, ket phi, is the sum over all the data points. And your core set is going to give you, some approximation given by the weighted sum. So the residual is obviously the direction that you want to go in with your next data point. So one thing that you might want to do is you say, well, choose the next data point to have the biggest inner product with the residual. And then I want to weight it by the sensitivity because, that information is still, that's basically how we can use that information. And then we can actually choose the weight. That's just a, basically how far in that direction do we want to go? That's a one-dimensional search problem, so we could use line search there. So that is a nice geometric picture, but if you look at that inner product, you're summing over all of the models, and you're searching over all the data points to do it. And so again, that's too expensive. So here what we do is a data reduction in the other direction. We say, well, instead of taking this inner product over all of the models, let me approximate this inner product in the model space by only looking at the samples returned so far by the quantum computer. And the quantum computer has returned t samples, then that will take time t on the classical computer. So the classical computer takes time t times the size of the data set. If t is pretty small, this is not much more than just sweeping once over the data set, which surely we were willing to do anyway. Like, we had to take the effort to acquire that data, so we should take at least the effort to read each data point once. And so the classical effort to find to do these inner products to augment the core set is quite reasonable, and the quantum runtime, on the other hand, is also not much more than doing a Grover search. You're doing a Grover search over models, and the inner loop is just the size of the core set, which again is not very large. So this is a pretty efficient algorithm. To prove that it works, a proof does not hold in the general case, but it certainly seems like a very plausible heuristic, and I think a promising one to look at. So I next want to move to kind of a special case of this where we can get an exact, maybe not exactly a special case, because it also changes things a little bit, but a version where we can prove that it works. Before I move on to that, any questions about this? Because I would say algorithm 1 was the non-adaptive core set. This is algorithm 2. I'm about to move on to algorithm 3. Good. So algorithm 3, here I'm going to, each time I'm solving a different problem, right? The first time maximum likelihood estimation, the second one, Bayesian inference. Now I'm going to solve a problem called saddle point optimization. And instead of my data set is x1 through xn, but now my set x is not going to be exactly that set. It's going to be the convex hull of all those points. So if you don't know convex hull, what it means is the smallest convex set that contains all of those points. Okay, so this green region is the convex hull of all these x1 through x9. And then y, my space of models, I need to change that a little bit too. Before, it was just this totally abstract set of items. Now, I need that to be convex as well. In fact, I need it to be the set of probability distributions over my m items. And I need f of xy to be linear in x and y. And now the problem that I want to solve is called a minimax problem. It's the best y for the worst x. So again, if I can think of y as models and x as data points, I want the y that does the best even over the worst possible x. So it's sort of like before I wanted to do well sort of on average over x. Now I want to do well in the worst case over x. And so you could think of applications to this, like if I want to stop someone from hacking into a system, and there are many possible ways they could hack in, I don't want to just sort of stop the average way of hacking in, because I have an adversary that's going to choose the best way to hack in. I want to be able to stop the best way for the adversary, the worst way for me. So it really has the feel of a zero-sum game. And von Neumann's minimax theorem applies here. We can exchange the order of the min and the max because of these conditions I've set. We could also write this as the minimum over x of the maximum over y of f of xy. So this is a general family of optimization problems. It includes, it's called the saddle point optimization or minimax optimization. It includes zero-sum games. And to be clear about the nature of the zero-sum game, I want to think of X as a classical set. So it's one where one player's strategies are described by records on a hard drive, and the other player's strategies are implicit and can be optimized over. So it takes some work, I think, to put things into that framework. And if I could editorialize a little bit, I would say that work is one that our community has done less of than we should have. We should do more of that work to complement the work we do on abstract quantum algorithms. Linear programming is another example of this. So we can think of the set of X as linear constraints on Y. So I want to optimize over Y subject to a bunch of find a point that satisfies a bunch of linear constraints. Each linear constraint is described by a record on a hard drive. And it's important here that the constraint be sort of succinct. So think of Y as m-dimensional. Each record needs to be much smaller in size than m, or just reading the whole thing would have wiped out our savings. So it has to succinctly describe some m-dimensional constraint. This occurs in kernel SVM. So this is L1 kernel SVM is an example of this sort of succinct constraint where you have a small data point that is mapped non-linearly to this larger vector, and then you want to do a hyperplane that best separates your yes from no examples. Another thing in this family is approximate maximum likelihood estimation. So if this minimum, the difference between a maximum likelihood estimation and this thing is that we have a sum over X instead of a minimum. But if that sum were dominated by the minimum, like the sum over all your data points were dominated by the worst data point, then that would correspond to this. And so this can be an approximate version of maximum likelihood estimation. So however you get to this problem, how can we solve it on a quantum computer? And here I'll be able to give you a provable speedup. And it follows this algorithm proposed 25 years ago by Grigoriadis and Kachayan. And to explain it, I'll use the zero-sum game framework, because I think that makes it very clear what's going on. So for a zero-sum game, let's think about the game of rock, paper, scissors. So the X player is choosing rock, paper, scissors. The Y player is also choosing from the strategy set. And this is the payoff matrix. And I've set it up so that we're seeing here the payoff for Y. Okay, so if X chooses rock and Y chooses paper, the payoff for Y is 1 because Y wins. And then to get X's payoff, you just put a minus sign in front because it's a zero-sum game. Okay, so this is a payoff matrix for y. And here is the algorithm by Grigoriadis and Kachian. I should say it's inspired by an algorithm that doesn't work. So, one algorithm that doesn't work, it's like, how little kids play soccer, where, they all run for the ball. An algorithm that doesn't work is the X player chooses some strategy, let's say rock, and then that will induce some payoff vector for the Y player. So this row here that I've highlighted. What doesn't work is choosing the best response. So the best response is paper. And then if X chooses the best response to that, that would be scissors. And the best response to that is rock. And that would just cycle forever, right? You can see that's just never going to converge. And there are many ways around this. One of them that works well is to introduce a little bit of randomness. So what we'll do now, Y is not going to choose the best response, but also is not going to play arbitrarily. Y is going to choose a response that is biased towards better responses. So let's say that X is Alice and Y is Bob. Bob will choose a strategy that has more probability, weighted by this distribution, e to the epsilon times the payoff vector. So slightly more likely to choose paper than rock than scissors. And so suppose that Bob happens to choose paper. Then we go in the other direction. We say, well, this induces a payoff vector for Alice. And she is going to do the same thing, except now there's a minus sign here because she's trying to minimize. And so suppose she chooses paper just because randomly she's not always choosing the best. She happens to choose that. Then we go back to Bob, but now he's responding to the sum of everything that Alice has done in all of the previous rounds. And so he's choosing from something, from the first two rows, from the combination of those. And as you do this over many rounds, you build it up, you start repeating rows. And so the good strategies are going to get repeated a bunch of times. And this is going to converge exponentially towards an approximate equilibrium. And what Grigoriadis and Kachian showed is that to get an error that's like epsilon times the largest entry in the payoff matrix, the number of rounds goes like the log of the strategy set divided by epsilon squared. So very good scaling with the total number of strategies. The epsilon squared is a little bit unfortunate. There are like 1 over epsilon algorithms, but they don't have the same property of using sparse strategies, which we need here. So this one is well suited to this hybrid architecture because there are T rounds of alternation, and T is not too big if epsilon is not too small. In each iteration, the classical computer has to go through the whole hard drive once, and on each record, the classical computer will need to look at T different strategies from T different values of Y. So T is pretty small. Each step here takes time, which is the size of the data set times T. The quantum computer, on the other hand, also in each round has to use Grover with order T calculations in the inner loop. So the total runtime is about T squared times the minimum you're prepared to do. The minimum would be going through the whole data set just once and doing an order 1 calculation each time, or doing Grover with an order 1 calculation in the inner loop. This is basically order T squared times that. So so this is a provable, everything about this runtime is provable, and it's not too much worse than what you would hope for. Any questions about this? And you can see how it has some similarity to this thing where, you want to kind of evaluate strategies just by looking at what the other player sent you, this Y1 through YT. So something similar is going on here. Okay, so these are a few strategies for using quantum and classical computers together. I want to briefly mention kind of the main, when people say hybrid algorithms, they usually mean this kind of variational optimization algorithm, where you have these variational parameters, T1 through TP. For example, QAOA, you would, is one example of this. Variational quantum eigensolver is another one. And you have a classical outer loop where you search over these parameters, and your quantum inner loop where you evaluate the cost function, or maybe you evaluate the gradient. And I think I kind of want to skip this part of my talk because, I don't know, I've been talking for a while, and yeah, I'll just say it very briefly. One other thing I've been working on is this sort of variational algorithm, where what we've looked at are the value of gradient observables. So you could say a 0th order algorithm is you search over these parameters. The quantum computer is used to estimate the cost function, and then you can do either some gradient-free algorithm, or you can use this to estimate gradients and do gradient descent. Or you could use a quantum computer to do a gradient estimation, and then you could do something like stochastic gradient descent, or some other algorithm like stochastic mirror descent. It's like gradient descent with a different norm. And these are called first order algorithms. This is sort of another approach to variational algorithms, to hybrid quantum classical algorithms, and usually that's what people refer to when they say hybrid algorithms. Or, for that matter, when they say NISQ algorithms, they often mean this. Just to go back to Ikai's question, yeah, and we'll get them. There are also second order methods, which have not been considered so much, but maybe they should be, and people are starting to do this with this quantum natural gradient, is sort of using some second order information. Yeah, so why does this not get stuck in local minima? I guess there kind of are no local minima. Maybe some intuition for why is, suppose I guess in general there are no local minima for this, but why does it do a good job? Suppose you're converging to something that is not an equilibrium for the zero-sum game. Then what that means is that one player has a better, has a strategy that would kick the butt of the other player, right? That would give that player a good payoff. And so what that means is when you look at the payoff vector, there's going to be one strategy that looks really good. And when you run this, that strategy will be exponentially weighted towards having a higher probability of being selected. And it has to compete, let's say there are n strategies, it has to compete with n other strategies. And that's why there's this log n here. After log n rounds, that single strategy will be more likely than the other n-1 put together. And so if there's some one good strategy that you're overlooking, after log n rounds, that one strategy will become very likely and will start appearing a lot. So I think that's sort of the intuition about why this thing works and doesn't get stuck, or more precisely, why it doesn't overlook some good strategy. With Zoom, I can answer your questions, but I can't see if you're nodding or not, but hopefully that answered it. Right, so a quantum computer can directly estimate. You can think of this as you're trying to minimize the expectation values of some Hamiltonian. So you can either directly estimate the energy or estimate gradients of the energy. And yeah, maybe I'll just say that, here's how a quantum computer actually does it. And what my student John Knapp and I showed is we gave some kind of rigorous performance guarantees for these various methods, like stochastic gradient and mirror descent, under various assumptions. I really don't want to get into the details of this. All I want to say is that how well these things do depends sometimes on whether your parameters, like this T1 through TP, naturally live in a space where you're using the 2 norm or the 1 norm. And it's not obvious to me which space is better a priori. I think empirically, like theory alone cannot guide that. And we also give an example, a very, very simple example where first order methods, like using gradients, provably do better than 0th order methods. We find that 0th order takes n cubed over epsilon squared time, and first order takes n squared over epsilon. Sorry, by time I mean like runs of your inner quantum loop. And the setting in which this happens is very, very simple. It's just your Hamiltonian basically has single qubit terms. There's a z term and then an x term. And the x term looks like 1 plus or minus epsilon. And this vector v is the vector that tells you whether it's plus or minus. And basically the gradient observables do much better than this than basically any 0th order algorithm. And the reason is, if you're close to the minimum, then the 0th order algorithm is measuring things that are close to the ground state. And in the regime where you're measuring the ground state, there's just going to be a lot of fluctuations in the actual energy. But there will not be so much, the gradient will not experience the same fluctuations. And I think I don't want to get into those details too much. I just want to kind of state that we have this, that we worked on this. And I want to briefly say, I should have made a slide about this, but didn't say it, is that these seem like two totally different approaches to hybrid algorithms, but they have some overlap. And if you go back to this this saddle point algorithm of mine, you can interpret that as a form of stochastic mirror descent, which is basically like stochastic gradient descent, but using a norm different than the usual L2 norm. Like you don't do, gradients are sort of an L2 norm kind of thing. If your natural norm is the L1 norm, then you get stochastic mirror descent. And that, it turns out, if you look at our at the zero-sum game algorithm the right way, that's using stochastic mirror descent. And I guess the difference, the only kind of additional feature of it is that it's very careful to keep things sparse. You know, I think when you do variational algorithms, we're not usually worried about having our solution vector be sparse. And the zero-sum game thing, it's very important that the vector be sparse. Okay, so yeah, I've gone on for more than an hour, so let me wrap up. Here again are the two archive links. Yeah, so in the first part of this talk, I focused on Grover a lot, but the same ideas really apply to any optimization algorithm. So no matter what, you have to worry about the size of your data set. And in general, when we're doing quantum algorithm design, I think we should always think about the fact that quantum computers are not going to replace classical computers, but they're going to supplement them. And so we should design algorithms to really think about their capabilities together. And this is another sort of hybrid algorithm. This is something that Garry Kasparov came up with after he lost to Deep Blue, or not came up with, but helped popularize something called hybrid chess or centaur chess, where you have a human and a computer together playing chess. And there was a period when the best chess ratings, humans reached some level, computers were above that, and then these hybrid, these centaurs, humans with computers together, would do better than even the best computers. Unfortunately for humans, now we do not really add any value to the chess-playing computer other than plugging it in and physically moving the pieces. But there was a period when humans could add some value. Now the computers are just so much ahead of us that we don't. Still, though, this points to the nature of the challenge for quantum computers is, how can we find a situation where both the quantum computer and the classical computer are contributing their unique strengths? And in the example I gave, the classical computers for a long time are going to be better at actually accessing the database the quantum computers might be better at doing the combinatorial search, and so we should try to divide up the tasks accordingly. Okay, I'll stop here. Thank you, everyone, for your attention.
Thanks, Aram. Yeah, so I don't know if we have a way to do applause, but
I see some cartoon hands, so thanks.
excellent.
Actually, before you have any questions, let me go get some water. I'll be back in 1 second.
Okay.
Yeah, there's a bar at the bottom of the screen where you can click reactions, and then there's an applause icon. What I think would be cool is if Zoom had an actual sound effect to go with that. That would be awesome.
There's also a coffee icon when you need a break.
Oh yeah, that's good.
Yeah. Does anyone have questions? If you like, you can enter them in the chat window, or you can just unmute. It seems like our group is not so large, so if you have a question, just go ahead and unmute.
I wanted to ask a question about this gradient estimation that you didn't have time to.
Yeah, sure.
Can you just show the slide where you have details of the gradient?
This one?
Yeah. So yes. The slide previous, the previous slide which you gave. Oh, yeah, this one. So do you get so in the output, do you measure only one component of the gradient, or do you like the output as a vector of the gradient itself?
No, right. Good, very good question. So yeah, there's a few things going on here. In the initial work, in some early papers, like Wecker, Hastings, Troyer, and I think is the one I'm thinking of, they observed already, like it's very natural to think you want to estimate a gradient, right? And they observed right away that the Hamiltonian has a sum of a bunch of commuting, like you can divide it into a few blocks in which all the terms commute, and you can just simultaneously measure all of those. And whereas the gradient, you get all these blocks that don't commute. And so you're kind of losing a factor of n right away by doing the gradient, because every run of your quantum computer just gives you one entry of the gradient. Whereas if you're doing energy measurements, you get to measure all the commuting terms all at once. And so that is why I think they and some other people thought the gradient is not worth it, because you lose kind of a factor of n right off the bat. And the other thing, right now, if you're not using if you're not using a NIST quantum computer, if you're willing to spend more time on your quantum computer and do more things in superposition, these are these papers I have down here, Stephen Jordan and by Gillian, Arunachallam, and Wiebe. They consider the regime where you can do phase estimation, right? So like, how should you measure, like, how do you measure H? One way to do it is you just like sample terms from H and measure those. The other one is you do phase estimation on it, and that will give you something more precise, but you'll also need more coherence time. And so if you're willing to do that, then you can get out the whole gradient vector, I think, with, and it's not too much worse than estimating the energy. But if you have limited coherence time, then it is more costly to get out the gradient than to get the energy measurement. And so that's why it's kind of surprising, or I don't know if you should be surprised or not, but that's why it's, I think, cool that you still can get an improvement, even if you sort of give up a factor of n here. Gradient methods are still better than energy measurement, like direct energy measurements.
And then if you just try to estimate this gradient by finite differences, it's not gonna, is it too noisy for
Yeah.
it to work? Yeah.
Well, actually, sorry. There's one more thing I wanted to say about this. This thing that's kind of cool that comes up when you do gradient measurement, which is I'm not answering your question, but I'll get to it. When you're doing, because you have all these terms and each term just gives you one little piece of the gradient, all of a sudden now you have an algorithm design choice of what weights you want to give to those terms. And that's also another kind of important sampling. Anyway, there's a lot of stuff in our paper about how do you make those choices, and they're really choices that are non-trivially different, and I think a lot of room for improvement. Sorry, say your question again.
So now you have a bunch of terms that you have to estimate the different measurements. But
oh yeah, sorry, I'm sorry. You said finite difference. Yeah. So why does that finite difference work? Right.
Yeah.
Good. Intuitively, when you my intuition for this is, suppose you have a superposition of, suppose the state that you create has a superposition of, I don't know, let's say ket A plus ket B, right? And A and B are different energies, very different energies. And what you want to do is you want to measure, you want to estimate the gradient on those. So maybe A and B depend on the parameters. So you have A evaluated at one value of t, and then A evaluated at another value of t. So you could call those, maybe A and A prime. So you want to measure the difference in energy between ket A plus ket B versus ket A prime plus ket B prime. And let's say A and A prime are pretty close in energy, and B prime are pretty close in energy. You would really like to measure the energy difference between A and A prime, and then measure the energy difference between B and B prime, and not add into that all the fluctuations you get because your measurements might sometimes return A and sometimes return B. So basically, when you're doing finite differences, your underlying, your quantum computer is just returning to you samples, and that includes quantum noise, right? Because quantum measurement doesn't just tell you the expectation, there's some fluctuations. And those fluctuations are going to add noise that you wouldn't have if you could do a direct gradient measurement. Does that answer your question?
Yes, thank you.
And that's not always the dominant source of noise, but sometimes it can be important.
Thanks.